Have you ever wondered, how can doctors see the bones inside the human body without surgery? How can an airport scanner look inside a suitcase without opening it? How can engineers find a tiny crack hidden inside an aircraft engine, even when the outside looks perfectly normal? And how can scientists observe extremely hot gas around black holes, millions or even billions of light years away from Earth? All of these things are connected to one invisible form of light, a kind of light that human eyes cannot see, but it can reveal things hidden inside the body, inside objects, inside machines, and even inside some of the most extreme places in the universe. That light is called X-rays. X-rays may sound familiar, because most people have heard of an X-ray scan. Some people have had a dental X-ray, some have had a chest X-ray, others have had an X-ray of an arm, a leg, or a broken bone. But what are X-rays really? Why can they pass through the body? And why do they create black and white images of bones? The answer begins with light. When we see sunlight, a lamp, or colors like red, yellow, and violet, we are only seeing a tiny part of all the light that exists. This full range is called the electromagnetic spectrum. It includes radio waves, microwaves, infrared light, visible light, ultraviolet light, X-rays, and gamma rays. Radio waves have long wavelengths and low energy. Visible light has shorter wavelengths. X-rays have extremely short wavelengths, much shorter than visible light, so they carry much higher energy. That high energy gives X-rays a special ability. They can pass through many materials that normal light cannot pass through. When normal light shines on your hand, it mostly reflects from the surface of your skin. Your eyes receive that reflected light, and your brain creates an image. So with normal light, we always see it outside. We see skin color, chip, fingernails, and small wrinkles, but we cannot see the bones inside. X-rays are different. Some X-rays can pass through skin, muscle, fat, and other soft tissues. But when they meet bone, metal, or denser materials, more of the X-rays are absorbed. This difference is the basic principle behind X-ray imaging. Imagine a beam of X-rays passing through your hand. In areas with mostly soft tissue, more X-rays pass through. In areas with bone, more X-rays are blocked. Behind the hand, there is an X-ray sensor. This sensor records how much X-ray energy passes through each part of the hand. Where more X-rays reach the sensor, it creates one level of signal. Where fewer X-rays reach the sensor, it creates a different level of signal. Then a computer turns those signals into a black and white image. That is why bones appear clearly on an X-ray image. The bones are not glowing. They simply absorb X-rays differently from the soft tissue around them. So an X-ray image is not a true color photograph of the body. It is a map of how X-rays pass through the body. Every bright or dark area represents a different level of X-ray absorption. Soft tissue, bone, and metal all create different signals. This is why, in a chest X-ray, the lungs often appear darker. The lungs contain a lot of air, so X-rays pass through them more easily. The ribs and spine appear more clearly, because bones absorb more X-rays. If there is metal, such as an implant or jewelry, it may appear very strong on the image, because metal blocks X-rays much more than normal body tissue. But where do X-rays come from? Inside an X-ray machine, there is an important part called the X-ray tube. This tube is like the heart of the system. Inside the tube, a heated filament releases tiny charged particles called electrons. These electrons are accelerated by a very high voltage. They move extremely fast toward a metal target. When the electrons hit the metal target, part of their energy is converted into X-rays. The X-ray beam is then directed outward. It passes through the body, or through the object being inspected, and reaches the sensor behind it. The whole process happens very quickly. In medical X-ray imaging, the exposure time is usually very short. The machine does not need to shine X-rays continuously for a long time. Only a brief exposure is enough for the sensor to collect the information needed to create an image. This is very important because X-rays are a type of ionizing radiation. Ionizing radiation means that it has enough energy to affect atoms. In some cases, it can knock electrons away from atoms. When an atom loses an electron, it becomes an ion. Because of this, X-rays must be used carefully. In medicine, X-rays are not used randomly. Doctors and technicians try to use the lowest dose possible, for the shortest time possible, while still getting a clear image. X-ray machines are also designed to limit the area being exposed. If only the hand needs to be scanned, the beam is focused on the hand. If only the wrist needs to be scanned, the rest of the body does not need to be inside the beam. If a dental X-ray is needed, the beam is focused only on the jaw or tooth area. That is why X-ray rooms often have shields, lead glass, lead aprons, or protected areas. Lead is very effective at blocking X-rays because it is dense and made of heavy atoms. When X-rays hit lead, most of that energy is absorbed, so lead aprons and lead barriers can help protect areas that do not need to be scanned. However, this does not mean that a normal X-ray scan is something to fear. In modern medicine, X-ray doses are carefully controlled. A normal X-ray scan usually uses a low dose and a very short exposure time. The important rule is simple. Use X-rays only when needed. Use them in the correct area. Use the lowest reasonable dose. And do not overuse them. Thanks to X-rays, doctors can detect broken bones, examine teeth, look at the lungs, find foreign objects, and monitor many conditions inside the body that cannot be seen with the naked eye. To understand how important X-rays are, let's go back to the moment they were discovered. In the late 19th century, the physicist Wilhelm Röntgen was experimenting with vacuum tubes and high-voltage electricity. During one experiment, he noticed that an invisible ray could make a fluorescent screen glow, even when there was an object between the tube and the screen. The strange thing was that this ray could pass through some materials, but it was blocked more strongly by bone and metal. Röntgen did not know exactly what the ray was, so he called it X-rays. The letter X meant unknown, just like an unknown value in mathematics. One of the most famous images in the history of science was the X-ray image of his wife's hand. In that image, the bones of the hand were clearly visible, and the ring on her finger appeared very strongly. That image shocked the world. For the first time, humans could look inside a living body without cutting it open and without surgery. It was a turning point. Soon after the discovery of X-rays, doctors realized they could use them to find bullets, check broken bones, locate foreign objects, and support medical diagnosis. Of course, in the early days, people did not fully understand the dangers of radiation. Many early users worked with X-rays without proper protection. Over time, science learned more about ionizing radiation, and safety procedures were developed. Today, modern X-ray machines are safer, more accurate, and much better at controlling radiation dose than early machines. This is a clear example of how science develops. A discovery may begin as something surprising. Then humans learn to understand it, measure it, control it, and use it more safely. But medicine does not stop with flat X-ray images. Another famous technology that uses X-rays is computed tomography, often called a CT scan. A CT scan works by rotating an X-ray source and a sensor around the body. Instead of creating one flat image from one direction, it takes many slices from many angles. Then a computer combines this information to create a three-dimensional view of the inside of the body. With CT imaging, doctors can look at layers inside the head, chest, abdomen, or bones with much more detail than a normal X-ray image. It is like the difference between seeing only the shadow of an object and seeing its internal structure slice by slice. X-rays are also used in dentistry. When a dental X-ray is taken, a small X-ray beam is directed toward the jaw or the tooth being checked. The sensor records the image of the teeth, roots, and jawbone. This helps dentists detect cavities, impacted teeth, root infections, and problems under the gums that cannot be seen from the outside. Some dental problems are hidden. A tooth may look normal on the surface, but there may be infection near the root. A wisdom tooth may be growing sideways inside the jawbone. A bone area may be damaged even though the gum looks fine. X-rays make those hidden problems visible. Now, let's leave the hospital and go to the airport. At airports, X-rays are used to inspect luggage. When a suitcase moves through an X-ray scanner, the X-ray beam passes through the outer shell and the objects inside. Fluid, plastic, paper, electronics, metal, and liquids all absorb X-rays in different ways. The sensor behind the suitcase records these differences and creates an image of what is inside. This allows security staff to quickly check luggage without opening every bag. Some modern scanners use multiple angles to create a clearer view. This helps separate overlapping objects and reveal items that may be hidden behind others. The principle is still the same as medical X-ray imaging. X-rays pass through an object. Different materials absorb X-rays differently. The sensor records the difference. The computer turns the data into an image. The only difference is that instead of looking at human bones, the system is looking inside luggage. In industry, X-rays have another very important role: non-destructive testing. Imagine a turbine blade from a jet engine. From the outside, it may look perfectly smooth, pure, and flawless. but inside, there may be a tiny crack, a small air pocket in the metal, or a hidden defect deep in the structure. If that part operates at high speed, high temperature, and high pressure, even a small hidden defect can become dangerous. So engineers need to inspect the inside without destroying the part. X-rays allow them to do exactly that. The beam passes through the material, the sensor records the image, and hidden defects can appear on the inspection scan. This method is used to inspect welds, pipes, turbine blades, machine parts, aircraft structures, engines, and many other critical components. A weld may look perfect from the outside, but inside it may contain bubbles, depths, or cracks. A pipe may be under high pressure, but have a weak area hidden in the metal. A machine part may be manufactured with high precision, but still contain a tiny defect that the human eye cannot detect. In these cases, X-rays become an engineering eye. They are not fooled by the outside appearance. They reveal the internal structure. In aerospace, X-ray inspection is even more important. Before a rocket is launched, it must survive vibration, heat, pressure, and enormous forces. Fuel tanks, weld, combustion chambers, nozzles, cooling channels, and structural frames all need very high reliability. A small crack in a weld or a hidden flaw inside a metal wall can become a serious problem when the rocket is operating. So X-rays help engineers look inside these structures without cutting them open. For satellites, X-rays can also be used to inspect sealed electronics boxes, wires, solder joints, and small internal components. Once a satellite is launched into orbit, it is extremely difficult to repair, so hidden problems must be found before launch. Here, X-rays do more than save time. They reduce risk. They increase reliability. And in aerospace, reliability is everything. X-rays are also used in scientific research at extremely small scales. When X-rays hit a crystal, they can scatter in special patterns. These patterns contain information about how atoms are arranged inside the crystal. From those patterns, scientists can understand the structure of materials, minerals, proteins, and many complex molecules. In other words, X-rays do not only look through large objects, they also help us explore the tiny world of atoms. A very important example is structural biology. Many molecules in living organisms have complex three-dimensional shapes. Their function depends strongly on their shape. If scientists can understand the structure of a molecule, they can better understand how it works. This is important for biology, medicine, and drug development. From an invisible form of light, X-rays became a tool for seeing the atomic world. But perhaps the most amazing use of X-rays is beyond Earth. In the universe, X-rays are produced in extremely hot and violent places. Gas at millions of degrees, neutron stars, supernova remnants, material around black holes, and even our sun can all produce X-rays. Human eyes cannot see this radiation. Normal optical telescopes cannot capture the full story from it. To observe the universe in X-rays, we need special telescopes. But there is a major problem. Earth's atmosphere blocks most X-rays from space. This is very good for life, because without the atmosphere, Earth's surface would receive much more high-energy radiation. But it also means that telescopes on the ground cannot directly observe cosmic X-rays. So humans must put X-ray telescopes in space. Above the atmosphere, satellites and X-ray observatories can detect X-ray photons from distant cosmic sources. These telescopes do not work like ordinary telescopes. With visible light, we can use a curved mirror to reflect and focus the light. But X-rays carry much higher energy. If X-rays hit a normal mirror directly, they usually do not reflect like visible light. They may be absorbed or scattered. So X-ray telescopes use a very shallow reflection angle. The X-rays do not hit the mirror straight on. They skim across the mirror surface at a very small angle. This allows the rays to be guided toward the sensor. Inside some X-ray telescopes, there are many thin mirror shells nested inside one another. This structure helps collect more X-rays and focus them toward the sensor at the back. The sensor inside an X-ray telescope must be extremely sensitive. It can detect individual X-ray photons coming from objects very far away. Then the data is sent back to Earth, where computers process it into scientific images. Many X-ray images of the universe are shown in false color. That does not mean the image is fake. The colors are used to represent data. Which regions are hotter? Which regions emit stronger X-rays? Which regions have higher energy? This allows human eyes to understand something that would otherwise be invisible. One of the most powerful sources of X-rays in the universe is the region around a black hole. A black hole itself does not emit light, because its gravity is so strong that light cannot escape once it crosses the event horizon. But the matter around a black hole can shine extremely brightly. Gas and dust are pulled toward the black hole. They spin at enormous speeds, become compressed, and heat up to extreme temperatures. In the hottest regions, this matter emits X-rays. By observing X-rays, scientists can study the area near a black hole, where gravity, speed, and temperature all reach extreme levels. If we only observe with visible light, we miss a lot of information. But with X-rays, the hottest regions in the disk of matter around the black hole become much clearer. X-rays are like a special language of the high-energy universe. Wherever there is extreme heat, strong acceleration, violent collision, or powerful magnetic fields, X-rays may be produced. Neutron stars are also strong sources of X-rays. A neutron star is the superdense core left behind after a massive star explodes. A neutron star can be smaller than a city, but more massive than the Sun. The matter inside it is compressed to an almost unimaginable density. Many neutron stars have extremely strong magnetic fields and spin very fast. When they emit high-energy radiation, X-ray telescopes can detect the signal from far away. Some neutron stars send out beams of radiation like cosmic lighthouses. As they rotate, the beams sweep through space. If Earth is in the path of the beam, telescopes can detect regular pulses. This helps scientists study the rotation, magnetic field, and environment around these strange objects. Supernova remnants also emit X-rays. After a massive star explosion,